Hello and welcome back to Math for Game Developers, where I took an embarrassingly long break, and I'm very sorry for that. I had a lot of deadlines, and then I had that talk, and at least you guys didn't get 4 months with nothing. At least you get to watch the talk. So the talk was really good, and then my computer died, and so I had to get a new computer. But we're back. And I have a lot of new software, and so it's much prettier now. Look at this beautiful line right here. I love this freaking beautiful line. And so we're gonna start with some very pretty lines. We're gonna do processor architecture today. Some really cool stuff. Let's get started. This is assembler code. This is Visual Studio, and you can see the disassembly. This is the disassembly right here, where it shows you the instructions, the processor instructions that correspond to the line of code that you've typed in, the C or C++ code that you've typed in. So here you can see right there, printf corresponds to these processor instructions: move, push, call, add, compare, call. And this shouldn't be very scary. It's exactly what it looks like. Move moves a piece of data from one place to another, right? Call calls a function, printf function. Add literally adds the number 4 to whatever's in this register. I think we talked about registers last time. And compare compares, XOR XORs. Okay, so these are the most basic instructions that your compiler writes your program into, and then these very basic instructions actually get executed directly on the processor. And so let's look at the steps for executing an instruction, bearing in mind that these are going to be very simplified steps. Most processors these days are vastly more complicated, but for our purposes, for understanding this concept that I want to show you guys, it's enough to reduce the instructions down to, reduce the steps down to these few steps. So step number 1 is fetch, which means to literally copy the instruction out of the highest level of cache. You remember we talked about caches in the last video, which was 4 months ago, which I'm still sorry for. There's actually a special cache called the instruction cache, the I cache, that holds instructions. And that's a level 1 cache, an L1 cache. And it's very close to the processor. So fetch just takes the instruction from that highest level of cache into the processor. Now it's in the processor. Okay. The second step is to decode, which is basically, what is this instruction? Is it a move instruction? Is it a compare instruction? Is it an XOR? Decode it so that you can figure out what to do with it. Step 3 is to actually execute the instruction. Execute. And so, if it's a move statement, then move. If it's a call statement, then call. If it's an XOR, then XOR. Do whatever it is that it's supposed to do. And then the final step is to write the result of that instruction. Like if you add, then you write the added number back into the highest level of cache. Okay, so then let's get a little bit better with this. We're going to draw a timeline. Time goes this way. And let's say we have a few instructions here. So we have instruction 1. And so first we are going to fetch instruction 1. And then when we're done fetching, we're going to decode instruction 1. And then when we're done decoding, we are going to execute, and then we are going to write the result. And so we do things, we go to the right. We fetch first, decode, so the time is going to the right here. Then when we're done, let's continue on to instruction 2. We got to wait until we're done with instruction 1. And then we can start fetching and decoding and execute. I'm just going to write X for execute and writing instruction 1. And then we do it again for instruction 3, fetch, decode, execute, write. And so on. We do this for all instructions. Now, I think we can do a little bit better than this. We can do this a little bit faster. And the key to knowing how to do it faster is to realize that each one of these steps is a different series of circuits in the processor. Okay? the fetch circuits are different than the decode circuits are different than the execute circuits, and so on. And so I'm just gonna draw it again. I'm just gonna show how we do it again here. Again, this is time. Time goes this way. So first we can use the fetch circuits to fetch the first instruction, and then we can use the decode circuits to decode the first instruction. But while we're decoding, the fetch circuits are now free, and so we can start fetching the second instruction at the same time as we're decoding, because we're using different circuits. And then as we're executing the first instruction, now the decode circuits are free, so we can decode the second instruction, and now the fetch circuits are free, so we can fetch the third instruction, instruction 3. And we can go on like this. We can have instruction 4. We can fetch that while we decode the third instruction, while we're doing all this at the same time. So you can see how this is much faster. Much faster. In the time that I finished one instruction up here in the slow way of doing it, I've finished like 2 or 3 instructions down here. Okay? So you see it's almost 4 times faster. So that we want to do it this way. And this way has a name. It's called the processor pipeline. It's kind of like a pipeline. It's like an assembly. It's like a factory, an assembly line, right? It's a pipeline. I don't know. However you want to visualize a pipeline. This is a pipeline. So this is very good. This is much faster. So now let's talk about a little gotcha here. A little gotcha. What happens if you have an if statement? Okay, you have an if statement, and then inside the if statement you have some kind of conditional. You have a conditional instruction, and depending on the result of that instruction, you don't know what's going to happen. You might have an else statement down here, okay, and it could be executing the stuff in here, or it could be executing the stuff down there. But the problem is, by the time you actually get to executing the conditional, that's here. Like this conditional is going to be this instruction right here, and this is the execute step. But we don't know if we have to execute this instruction 2 from here or instruction 2 from there. And we could execute instruction 3 from here or instruction 3 from there. We don't know which one of these sections of code we have to execute instruction 2 from until we get to this point right here. That's a problem because that will cause a stall in our pipeline. This right here is called well actually, this is probably a better picture of it. This right here is called a stall. We want to avoid this picture up here where we have to wait until the end of our previous instruction to start the next instruction. That's a stall and we want to avoid it, okay? So what does the processor do? It doesn't know whether to execute this part or that part. And so it actually just guesses. It just takes one of these parts and does it, okay? And it doesn't do the right part. It doesn't write the result back into the cache until you get to this execute, and then it knows whether or not it guessed correctly. If it guessed correctly, then it just writes everything, in one huge chunk. It just goes ahead and writes it all. But if it guessed incorrectly, then it has to back up. It's got to say, well, crap, I fetched and decoded and executed instruction 2, but that was wrong, and this is wrong, and this is wrong, and then it has to go to the other side of the other part of the code and execute that instead. And this is very bad. And it is called, it has 2 names. It's called a bubble. A bubble because there's now a bunch of open space that we could have been using to execute instructions. Or it's also called a branch misprediction. Prediction. This right here is a branch, and this right here is a branch. This is the true branch, and this is the false branch. Oh my God, this is so pretty. I love this new software. And so this is a branch prediction or a bubble. And now we're going to go to the code section and we're going to figure out exactly how we can design programs to avoid branch misprediction so that our programs run a lot faster. Not our programs, our games, because we're game developers. We want to know how to make games that run faster. So we're going to the code section now. We're going to figure out how that works. See you in a moment. Okay, welcome to the code section, and no, everything is different. Everything is changed. I'm scared. I don't like change. Okay, calm down. It's all the same. It's the same stuff. It's still me. I'm still George. I'm going to explain everything. Hopefully everything will become clear by the end of this explanation. Okay, it's a really cool demonstration. So here we go. We are going to build a particle system, okay, where each particle either has or does not have gravity associated with it. So, for example, a puff of smoke would not have gravity associated with it because you want the smoke to just float around and not fall. But then, like a fleck of concrete, you shoot a wall and concrete flies out of the wall, and so the concrete should fall to the ground. It should have gravity applied to it, okay? And so our particle system should be able to simulate both types of particles. And so that's where, this is our update loop, excuse me. And so we just have a little if statement here. If the particle has gravity, then we apply the gravity to the particle. There it is. There's the gravity. There's the particle right there. It has gravity. Okay. And this is the if statement that is going to be mispredicted. We're going to show the difference in performance between when this is mispredicted and when it's normally predicted, when it's well predicted. And by the way, if this code does not, if you do not recognize this code with the position being updated by the velocity times the frame, then you can go and watch one of my earlier videos, the frame time update. Let's see, I'll definitely link to it here, and that will make everything clear. Okay, so where was I? Yes, so we update every particle based on whether or not it has gravity. And let's see what the particles look like, okay? This is where we initialize the particles. We create 10,000 particles and we spawn them all, okay, which just means we add them to our list of particles, we give them position and velocity or whatever. And then we go through our list of particles, every one, and we assign each one to either have gravity or not have gravity randomly. And the reason we do this is because in a naive implementation of a particle system, you might have many particles being created and destroyed over the course of your game, and you just put them all in one big bag, and they don't really have any order to them because they all got kind of created interspersedly. Okay. So they all just go in this one big thing, and a particle without gravity might be next to a particle with gravity and so on. And so when you go through this list, right here, the processor is going to guess at this if statement, just like we talked in the previous video. It's going to guess whether it should do or not do the stuff in the if statement ahead of time, right? In its pipeline, okay? And it's going to base that guess on what it did last time. But last time was random. And so last time is not a very good guess for this time. Half of the time we're going to get it wrong. And so we're going to have a lot of branch mispredictions for this if statement right here. Okay, so let's see that at work. Let's build that. And oh, by the way, I have -02 enabled, which enables all optimizations. Okay, that's what -02 means. It means give me a high level optimization, because we're going to show that the compiler is not smart enough to fix this problem for us. It's not smart enough to fix branch predictions for us, even with all the optimizations on. So, okay, so we're going to build this. Let me see, main, okay, good. It rebuilt my main. And yes, I know this is a console. It's very scary, but it's really not that difficult. I'm running the debugger now, and I'm going to type the run command. That's really all I'm doing. I'm running the program in a debugger. Okay, and there it is. It gave us 984 milliseconds to simulate. I simulated 333 seconds really quickly, and it took 984 milliseconds to do that simulation. Okay? So now, coming back to main.cpp, we want to improve the prediction of this if statement. So here's what we're going to do. We're going to group all of the particles with gravity together, and all the particles without gravity together, okay? And I've set that code up right here. So we're going to split the particles in half, And all the particles without gravity, we're going to put first. And then all the particles with gravity, we're going to put second. So then what happens when you go through this for loop is, this actually becomes a very good prediction of whether or not the particle has gravity. So when the processor gets to this point, it looks at the previous time that this ran, so the previous particle, and it says, did that particle have gravity? Well, we grouped all the ones with gravity together and all the ones without gravity together, and so this is now a very good predictor of whether or not it has gravity. It's almost always accurate, an accurate predictor. And so let's take a look at the results now. Okay, we quit from the debugger, we rebuild. It should rebuild our main file. There it goes. We run the debugger again, and I type the run command to run, and now it simulates, and it runs it in 614 milliseconds instead of 984. Now, I'm not very good at math, but I think that's like a 30 or 40% increase in performance. And mind you, we did not change our update function at all one bit. All we changed was the order of our data. We just organized our data. We sorted our data, and we got this huge 40% performance increase. Not 1 or 2%, but 40%. That's huge by just reorganizing the data. Okay? No algorithmic changes at all. I think that is amazing. Just astounding. Okay, so and there's one more thing I want to look at, which is the for loop. Look at the for loop here. Okay, notice that we have I is less than particles, right? That's a condition. That's like a little if statement, isn't it? If I is less than particles, then repeat the for loop. So this is another conditional, but notice that is almost always the same, right? When you're chugging through this loop, I is almost always less than particles until the very last particle, and then I gets incremented and becomes equal to particles, and then the condition is false. So you get a misprediction only on the very last one, and for the rest of the time, the processor is correctly predicting that we should continue down the loop. So this is why loops are so fast, right? You only mispredict the very last thing in the loop. Okay, so I think that was I am constantly amazed by this sort of thing, and I like it. So obviously, so I was really happy to show this demonstration to you. I hope you liked it too. Next week, I think we're going to finish up the optimization series, and we're back on track with these videos. And but for now, I'm going to go play some more TIS 100. See you next time.